Assalamu alaikum. I welcome you all to another lecture of power electronics. In the last lecture, we discussed about the Sap converter, which provide the same transfer function as that of a buck-boost converter. However, it has an added advantage that both the input current and the output current are continuous. In today's class, we will discuss another non-isolated type of a converter, which is known as the SEPIC converter. So let us start with this particular converter. SEPIC stands for single-ended primary inductance converter, and this is the most simplest form of a converter which can be obtained by having a cascade connection of a buck converter and a boost converter. So if we cascade the two converters such that we have an input here, and there is the first converter with some gain G, GV, and we cascade another converter here with gain G, let us say this is G1, this is G2, then on the output side, the overall gain of these two converters which are connected in cascade, the overall gain is a multiplication of the gain of the first converter and the gain of the second converter. Now the derivation of a SEPIC converter based on the cascaded connection of a buck converter and a boost converter is well explained in a book, Fundamentals of Power Electronics by Robert W. Erickson. Now in that particular book you can go and see what are the different methods which are used to develop new circuits. However, in this particular class, my intention is not to explain the procedures and the circuit manipulations which lead to the development of new converters. Rather, we will only analyze the SEPIC converter based on the knowledge that we have acquired in this whole module. That is, we will establish the circuits with the switch on condition and switch off condition. Thereafter, we will write down the equations based on the Kirchoff's voltage law and the Kirchoff's current law for the inductor voltage and the capacitor current, and thereafter we will derive the transfer ratio or the voltage gain of this particular converter. Further to this, we will also develop the expressions for the inductance requirement for this converter and the capacitance requirement of this converter, and at the last we will go for the switch realization and we will establish the switch stress for this particular converter. So let us start with the basic circuit and develop the equivalent models. Let us annotate this as well. Let us say this is Vs, this is plus minus VL1, and this is the inductance L1, and the current flowing through this branch is IL1. This is the voltage across this switch, and let us say this is Vs1, this is Vs2, and this is switch S2. This is the capacitor C1, so we have this Vc1, this is C1. This is plus minus VL2, this is L2, and therefore using the passive sign convention, the current is entering this positive terminal. So this is IL2, this is IC2, this is I0, and this is the resistance R. So this is the voltage V0, and this is the VC2. Now one thing we should notice in this particular circuit that we have shown two separate single pole single throw switches for this particular converter. Now we still have no information as to which switch is an active switch and which switch is a passive switch, but we require to have two switches which work such that when S1 is on, then this S2 is off, and vice versa. When this S1 is off, then the switch S2 will turn on. Consequently, the logic between this S1 and S2 is actually a complement. So consequently, this S1 is equal to the complement of the S2. So for this switch 1 on condition, we can draw the circuit as follows, that since the switch 1 is on, so this is the circuit here. On the output side, the capacitor current IC is in this direction, and this is I0. This is of course V0. This is R. This is plus minus VC1, plus minus VL1. This is Vs. And this is plus. This is minus. This is VL2. This is IL2. We need to be consistent with the defined polarities. Whatever polarities we have defined for the inductor and the capacitor, we should stick with those polarities for the analysis in switch on position or in a switch off position. So if we apply the Kirchoff's voltage law in this loop, it will give us the expression for the voltage across the inductor L1. So that is equal to minus Vs plus VL1 is equal to 0. So this VL1 is equal to Vs. Let us say this is my equation number 1. On the other side, if I apply the KVL in this loop only, then we have plus Vc1 minus VL2, that is equal to 0. So VL2 is equal to sorry, this is Vc1. So VL2 is equal to Vc1. So let us say this is my equation number 2. Other than that, we can see here, if I apply the Kirchoff's current law here, then I have IC plus I0 is equal to 0. So IC, if I apply this small ripple approximation, that is equal to minus I0, and that is equal to minus V0 over R, and this is my equation number 3 for this switch on condition. For the switch off condition, let us draw the circuit for the switch off condition. So when switch 2 is on, then we have this switch 1 in off state, and therefore the equivalent circuit that emerges here is this one. So this is the circuit. This is VL1. This is plus minus VC1, plus minus VL2, plus minus V0, plus minus VC2, and this is R. So now if we apply the KVL in this path, then we can find out the voltage across the inductance L1. So VL1, so this is equal to minus Vs plus VL1 plus Vc1 plus V0, that is equal to 0. So VL1 is equal to Vs minus V0 minus Vc1. This is my equation number 4. And for this inductance L2, we will apply the Kirchoff's current law. We will apply the KVL here. So this becomes equal to VL2 plus V0 is equal to 0. So this VL2 becomes equal to minus V naught, and this becomes my equation number 5. If we apply the Kirchoff's current law here, then IC is equal to this current, let us say this is ID, that is equal to ID minus I naught, and that is equal to ID minus V naught over R. So this becomes our equation number 6. Now if you notice one thing here, that we have no information about the voltage across this particular capacitor C1. So in order to find out the voltage across the capacitor C1, we can apply a KVL in this whole loop. So if I apply the KVL here, then this is equal to minus Vs plus VL1 plus VC1 minus VL2, that is equal to 0. And we have earlier discussed this, that over a period of one switching cycle, the net voltage across an inductor is equal to 0. So the volt second balance in a steady state circuit is always maintained for the inductor, and therefore this VL1 and VL2 are equal to 0, and consequently this VC1 becomes equal to this Vs. So based on this particular information, we can modify these equations such that this VL2 becomes equal to this Vs, and this becomes my equation number 2a. And in here, this equation number 4 becomes VL1 is equal to Vs minus V naught, and that is equal to minus V naught, because this is cancelled by this one. So this becomes my equation number 4a. So if I summarize these 4 equations, which represents the voltage across the inductor L1 and L2, then one thing is very sure, that for inductance L1, VL1 is equal to Vs during the time we have applied the signal to the switch, which is the DTS, and for the DTS to the TS, this becomes equal to VL1 is equal to minus V naught for the time period DTS to the complete time period TS. Similarly, for the inductance L2, this VL2 is equal to Vs between the time 0 to DTS, and this VL2 becomes equal to minus V naught for the time we turn on the switch S2. Now this is very surprising, because for both the inductance and for both the inductances L1 and L2, the volt second balance are exactly the same, and therefore if I draw the waveform of the voltage across these inductors, then the very evident thing is that we have, this is Vs and this is DTS, and this is minus V naught and this is D dash TS. So if I apply the volt second balance here, so this becomes equal to VSD TS minus V naught D dash TS, that is equal to 0. So what we get here is that V naught over Vs is equal to D over D dash, and this V naught over Vs gives you D over 1 minus D, and this is exactly the same expression as we have seen for a buck boost converter, but we do not have an inverse polarity on the output. So this is quite an advantage which makes this particular converter suitable for a lot of applications where we require to either step up the voltage or we require to either step down the voltage. So this polarity inversion is not an issue for a SEPIC converter. So the same can be obtained by actually plotting the voltage here. So this is also VL1 and this is also VL2. So both gives you the same value of the transfer function. As the next step, let us plot the inductor current waveforms. So for the inductor current waveforms, we do know that if a converter is operating in a continuous conduction mode, then we have an average current IL1 for the inductance L1 and IL2 will be the average current flowing through the inductor L2. From this average current to the peak, we have half of the delta IL, which is the peak to peak ripple, and half of the peak ripple is below the average value, and which starts from the minimum current for minimum value of the inductor current. Here we have this Imax. Now the slope of this rising slope is during the time the switch is on, that is during this DTS, and for L1 you can see here that this VL1 is equal to Vs and this is equal to L di over dt, and therefore based on this expression we can safely say that this di over dt is equal to Vs over L. So that is equal to Vs over L. So based on this peak to peak ripple, which is equal to the sum of these half of delta IL and this half of delta IL, so the combined delta IL, which is the peak to peak ripple, is equal to Vs over L into DTS, and that is equal to Vs d over Fs into L. And based on this thing, this is L1, so this L1 becomes equal to Vs d over delta IL1 into this Fs, and this gives me a value of the inductance which is required for a given inductor based on the ripple component of the inductor current. And because the slope for this IL2 is also same, so this holds true for the inductance L2 as well. Now one thing is for sure, that this IL1 is always expressed as a percentage ripple component of the average inductor current flowing through the inductance L1 or L2. This means that even if I specify that for a given converter we have this delta IL1 is equal to delta IL2, that is equal to, let us say it is 20%. This is 20% of the average current IL. So we should know what is the value of this IL, because if we do not know the average value of this IL, we are not able to calculate this particular component. So to find out the value of this IL, we assume that the P in is equal to P out, so that we have a lossless converter. So what is the input power? P input is equal to Vs into Is, and based on this circuit we can see that this IL1 is also the source current, which is Is, because they both are connected in series. So therefore I can say that this is equal to Vs into IL1. What is the P naught? P naught is equal to V square over V naught square over R. If I substitute these two in here, this becomes Vs IL1, that is equal to V naught square over R, and this gives me the average current flowing through the inductance L1, and IL1 is equal to V naught square over Vs into R, and this is the average current flowing through the inductance L1. To find out what is the average current flowing through the inductance L2, we will apply the KCL at the node where we have this C1 L2 and S2 are common. So I will apply particular node. Let me copy this one. So here we are. So what I am trying to say here is that we have to apply the KCL here. So apply KCL here to find IL2. So for this KCL, the current entering in a node is assigned a negative value and the current leaving the node is assigned the positive value. So based on this particular convention, this IL2 minus IC1 plus ID or plus IS2, that is equal to 0. So this IL2 becomes equal to IS2 minus IC1. Now what is the value of this IS2? This IS2 has two parts. It consists of IC1 and the current I0. So if I plug it in back in here, then this IL2 is equal to IC1 is equal to IC2 plus I0 minus IC1. And we have a good knowledge about this, that for a steady state operation, the capacitor, the net charge or the charge second balance on a capacitor is equal to 0. So the average current through this capacitor should be equal to 0, and therefore through the charge second balance, this IC2 and IC1, they both are equal to 0, and consequently we have this IL2, this becomes equal to the I0, which is not difficult to calculate because the voltage is also known for a given duty cycle value and the value of the load resistance is also known to the designer. So next, let us find out the value of the capacitor. For the switch on and the switch off conditions, we have the value of this IC2 as well as the value of this IC1. So during the time DTS, let us use this figure to identify the values of the capacitor current during the time the switch 1 is on and during the time when switch 2 is on. So when we have the switch S1 on, then we have the IC1, it becomes equal to minus IL2, or that is equal to minus IL2, and that is equal to C2 dV by C1 dV by dt. Also when we have this switch connected with switch 2 is connected, then this IC1 is equal to, it becomes equal to IL1, that is equal to C dV by dt, C1 dV by dt. Similarly, during the time when we have this switch on, this switch 2 is off, and therefore by applying the Kirchoff's current law, we know that this IC2 is equal to minus I0, and that is equal to minus V0 over R, and this is equal to C2 dV by dt. And for this time DTS, this IC2 is equal to ID minus I0, and that is equal to C2 dV by dt. Now on a similar pattern, if we draw the waveforms, then we have, this is, let us say this is for IC1 and this is the DTS time, and here we have the D dash TS time. So this slope is what? It is equal to this is VC1. So this slope is dV over dt, and that is equal to IL2 over C1. So if we say that this is the total ripple delta VC1, then this delta VC1 is equal to IL2 over C1 into D into DTS, and that gives me the value of C1 as Fs into delta into delta VC1. Now, if you notice in this expression, this IL2 is again not a function of the input and the output, and therefore we need to express it by using this expression which is equal to this I0. So if we use this expression, then this C1 becomes a function of the current I0, which is again a known quantity to the designer. So C1 is equal to I0 into D, and this can be substituted as I is equal to V0 D over R into Fs into delta VC1, and this can be further written as R Fs into delta VC1 over V0. And this, if you do the calculation for the capacitor C2 using the same concept, then this is also equal to C2. So the value of the C1 and C2 is also same, but for the C2 this delta VC1 will become equal to the delta VC2. Now in the next step we need to understand what are the switches that are used for this particular converter. For that, let me again use this particular diagram. So for this S1, if this is A and this is B, then VSW is equal to VAB. B is grounded. What is the value of A in here? What is the value in A in when we have this S2 available? That is equal to, when we have the switch S2 available, then VAB is equal to, we can apply the KBL in this loop such that the expression is minus VSW plus VC1, ignoring the drop across this switch S2, this is plus VC2, that is equal to 0. So VSW is equal to the sum of the capacitor voltage VC1 and VC2. And we have earlier noticed that this VC1 is equal to Vs, right? So we have earlier seen this here. This VC1 is equal to Vs. So this V switch is equal to Vs plus V0, which is the output voltage, which is a positive quantity, and therefore the device that can be used to realize this switch S1 should have a positive voltage blocking capability. For the current, when we turn on this switch S1, then the current flows through this positive terminal, and therefore this S1 must have some characteristics with a positive current and a positive voltage blocking capability that can be realized either by using a BJT or a MOSFET or any other device like an IGBT. For this switch S2, this is S2 for, so if we have this switch turned off, let us say this is A and this is B. So let us apply the Kirchoff's voltage law on this loop. So if I apply the KVL here, so that becomes equal to Vs2 plus Vc2 plus Vc1, that is equal to 0. So the Vs2 is equal to minus Vc1 minus Vc2, and that is equal to minus Vs minus V0, which says that this switch S2 can only be realized with a device which is capable of blocking the negative voltage. As far as the current is concerned, when we turn on this switch, then the current enters this positive terminal, and therefore for the switch S2 we require to have a forward current flowing capability and a reverse voltage blocking capability, which is only available in a device which is known as diode. So if I draw the circuit now, let me paste the circuit here. So we have Let me replace these two switches now. So because this is, here we have the diode and here we can use a BJT, or I can use an IGBT or a MOSFET. So as far as the switch test is concerned, for this particular converter, the switch test switch test can be realized through these equations. For this particular converter, the active switch has to block the sum of the input voltage and the output voltage. And for the switch 2, the voltage blocking is the sum of the input voltage and the output voltage. So the minimum rating of these two devices should be greater than the sum of the input voltage and the output voltage. As far as the current is concerned, the current rating of these two devices for this IQ1 should be greater than the sum of the inductor current IL1 and the IL2, and for this switch ID, it should also be equal to greater than the IL1 and this IL2. So lastly, let us draw the key waveforms for this particular SEPIC converter. Let me paste it again here, so that we can have more clarity here. So for this I1, this is the inductor current, this is the IL1, the IL2 is also of the same shape like this one. However, in here we have the average value, which is equal to V0 I0 over V0, the average inductor current IL1, V0 square over VSR, so that is equal to V0 square, and this average current for this IL2 is equal to this I0. Next we have the current through the capacitor C1. So C1 has this type of the current shape. So it has the IL2 in opposite direction when we turn on the switch S1. So this is nothing but this IL2, and after it is turned on, the switch S2, this becomes the down. It takes the downslope of the inductor current IL1. So this is the IC1. As far as this IC2 is concerned, this IC2 is equal to minus I0, and after this diode is turned on, it becomes equal to the, sorry, let me just draw it again so that we have the consistency with the zero time here. That is equal to the sum of IL1 and this IL2. As far as the switch S1 is concerned, the S1 has to take down the value of the current flowing from this IL1 as well as the current flowing from this capacitor C1, which is the current IL2, and therefore it shall have this type of a value where this is equal to IL1 plus this IL2. This is the IQ, and for the diode we have this current, and this is equal to IC1 plus IL2, and this IC1 is the current which is coming from here, so that is also equal to, this is IL1 and this is equal to IL2, and this is the current through the diode D. Now in certain cases the L1 and L2 usually come out to be of the same value, and when this happens, we can replace this inductances L1 and L2 by a unity transformer of the turn ratio 1:1, which acts like a coupled inductor. If this happens such that we have this L1 is equal to L2, then we do know that dIL1 over dt is equal to dIL2 over dt. So therefore we can go for a solution which is known as the mutually coupled inductor. Mutually coupled inductor can be used in the form of a 1:1, a 1:1 transformer. So if this happens, then this particular SEPIC converter can be realized using this is C1, this is L1, this is L2, which is equal to this L1, and this is a 1:1 transformer. Here we have the diode, and here we have the capacitor C2, and this is R, and this side is also grounded. So this is another alternate representation of a SEPIC converter, which is based on the mutually coupled inductors. So I hope that you have understood this concept of a SEPIC converter very well. I advise you to go through the simulation process and verify that the currents which are flowing through each of the component of this particular converter are exactly the same as we have drawn in this today's class. Thank you very much. Allah Hafiz.